Q is unique. And I guess so. I guess the answer is yes. Then you do get a unique P and Q because the Q will be unique. So the Q will come from the H sequence.
But not all the matrix satisfy this condition.
Oh no. So I mean, not all lower triangular matrices will be Riordan arrays, which is another question. How do you test whether a given lower triangular matrix is a Riordan array? And I'm not sure there's in this this article here. He talks about ways of trying to work out whether a given lower triangular matrix is a Riordan array, but it's I'm not sure if there's any sort of formal results or sort of formal method for working it out.
I mean, is there like a inverse map that maps the PQ to a matrix? So you have like a explicit definition, but if I have like a matrix, which is a Riordan arrays, how do I get P and Q from that? What's the inverse of that map?
Right. Oh, I see what you mean. So, well, to specify, if you have a matrix, you must have a way of specifying, because it's an infinite matrix, you must have a way of specifying all the entries in the matrix. Which means that you would have an A sequence and a Z sequence. I guess that's the logic. So otherwise, yeah, how do you say what? So, yeah, as long as you have an A sequence and a Z sequence, then you can get P and Q uniquely.
For the Riordan, is there any element with the finite order besides the identity?
Oh, when you say, sorry, what, what do you mean finite? Sorry, what do you mean finite order?
When I mean, if it keep modifying with itself, then it is identity again. You know, you apply operation, right, to the same.
Oh, order as in a group, the order of a group element.
Yes.
Okay, so remind me what the order of a group element is.
Oh, you just ask for an element with a finite order. Like if for example, I pick an element, let's say.
Like it's multiplying itself.
Right. Oh, right. I remember now. Yes. Oh, if you multiply itself, you get the identity. Oh, I see. Yeah, I don't know. Yeah, to be honest with you, I don't know. Yes, interesting question. Okay, is there anything which you multiply itself gives the identity matrix?
I mean, at some point.
Well, it would be if you had minus -1 all along the diagram is not in the Riordan group because it has to have 1 as the top, as P0 has to be 1 in the Riordan group. Yeah, I don't know of any example where you multiply itself and gives the identity.
So you did mention like you have some identity came up in your research that you need to use this technique.
Oh, I see. Yes. No. I mean, yes. The reason we came across this Riordan array was that we got this number triangle in a tiling problem, and Ken somehow noticed that if you reverse the rows in our number triangle, then you end up with a Riordan array. So that was the connection. I mean, we can prove that. It's not that difficult to prove, but we haven't really worked out if there's some significance to that. If it's, you know, for example, is it true generally that with this type of tiling problem, will you always get a Riordan array if you reverse the rows? We haven't worked out. But,
that's why.
But that was it. That was the original motivation for looking at this. Yeah. Yeah, I mean, funnily enough, we got this number triangle. We put it into the search in the OEIS, and it didn't come up with anything. but it turned out we later found it was there, but the problem was the number triangle has some zeros along the diagonal, and the person who put in the series before had omitted those zeros.
Skip zero.
Yeah, so it's not actually, it sort of doesn't mention anywhere in the instructions whether you're meant to include those zeros along the diagonal or not. So that's a bit of a problem with the encyclopedia at the moment, because some series do include the zeros and some series don't. So that's why we didn't find it.
You put all the entries on the lower triangle.
Yeah, yeah,
Yeah, that's common.
yeah. But actually, Ken actually found a Riordan array which had every other element was negative. I'm not quite sure how he managed to find that. So before we actually understood a bit more and actually looked at the relevant paper, we had to actually prove why our triangle was the same as this Riordan array if you mess around with the order of the rows and mess around with the signs. And it turned out that we found another Riordan array mentioned in the paper which was exactly our triangle but with the rows reversed. But yes, the triangle actually counts, well, if you add up the rows you get the Fibonacci number squared. So that was, but the person who wrote the article about which is actually Paul Barry, who I mentioned, also noticed this about the Riordan array.
Is there any way to recognize the given matrix?
That's what I'm wondering myself, yes. Basically, it will be a Riordan array if there's an A sequence. So if you can write a lower row in terms of the row above by adding in that specific way, then it will be a Riordan array. And also the first column you have to specify.
If it's not,
Then I guess there's no, yeah, I think it has to have an A and Z sequence. I think the two things are equivalent.
So if it doesn't have that way, it's not really.
I believe so, yeah. So, yeah, what I haven't talked about, presumably, if you're given P and Q, you should be able to work backwards and get A and Z. So, I mean, presumably, you can actually use this in reverse. So we've got a relation between Q and A here, but suppose you know Q and find A, then you'd have to solve that sort of functional equation to get A.
So it's an if and only if condition. If you
I think so, yeah. I believe so, yeah.
maybe it's not too difficult. Yeah, this is what I asked you at the beginning. Like, say if you have an P and Q, can you solve for AX?
Well, you only need Q, so yeah, you only need Q to find A. Once you've got A, other way around, then you want to find Z, which would be easy in this case, wouldn't it? Yes, because you found Q, then you'd be able to find what Z is.
Like you can you go back? Like you solve the second equation to get the A, right?
Yeah, so if we're doing what you said, yes, if you start with P and Q and you want to find A, then you need to solve this equation to find A, yeah. Which is not that easy, I guess.
It's opposite.
It's, whatever you call it, yeah. But, yes, this is ringing a bell. There's something, is it Lagrange? Yes, yeah. So yes, and on another YouTube clip about Riordan arrays, they, he sort of gives an introduction which mentioned this Lagrange inversion as a sort of motivation behind Riordan arrays. So it's all connected. Yeah.
I think the This is the exact form of the Lagrange equation.
Right, yeah.
Oh, okay, that's, I see. Okay, okay. So